recording. Yes. Okay. So optimization. So until now, what we've looked at is just problems in fully observable and deterministic and static environments, meaning that we have access to the entire problem space. Like we never have Dijkstra's where we can't see the entire graph and we're only seeing what's around us. So that's one of the things that we've looked at so far, or even with A star, we have access to the entire thing. The other thing we can guarantee is that the graph won't change. If the costs on the graph start changing while we're doing the algorithm won't work. So it's been static, it's been fully observable, and it's been deterministic. However, these, as we will see today, aren't always possible with every single type of problem. And what we're going to look at is how we can still optimize, still find a good, reasonable solution to problems when we don't have a fully observable, deterministic, and static environment, which in most cases is actually what happens. So, optimization problems are those where one seeks to maximize or minimize an objective function, or even multiple objective functions, there's no limit, and while you remain within a set of constraints that are given, or you can make yourself, to ensure that the solution is feasible. So here's a question. How can we find the point on the line y equals 2x minus 4 that's closest to the origin? I don't know if you remember this one from Leonardo's slides. He used this question as well. What is the optimization? How would you formulate this as an optimization problem? Okay, right. So Shay's saying minimize the Euclidean distance between a point, so the line coordinates x and y, to the origin. Yes, that's, yep. We want to minimize the Euclidean distance. So the Euclidean distance would be the objective function, yeah, as you've said, and we would want to minimize that. So that's exactly what we would be doing. So if I open this up, we can see the solution. So to do this, we've used calculus here, so differentiation. We'll look at some problems with this, and I want you guys to do a specific problem, which you should be able to use your A-level maths knowledge on, because you can do it using differentiation. And then the reason I want you to do it is because we can use that to then see how other algorithms like hill climbing and simulated annealing works, which we'll come across later, with the same problem and then compare them. So I want basically to give you guys a problem which, where did it go? It was about a net and a box and a cube. Hang on, let me just try and find the problem. Okay. All right, I'm going to paste the problem into the chat so everyone can see it. And I'll also put it onto the screen as well so the recording can see it as well. Okay, so here's the problem. I hope everyone can see that in the chat. It should be uploaded now. And yeah, maximize the value. Find the corner value of the corner cut length to maximize the volume of the box formed with this net. So here, you can think of this like we're forming a box, right? We're forming like a suitcase almost. And well, when we go traveling, unfortunately, airlines have luggage dimension restrictions, right? So we are restricted to having dimensions of 64 centimeters by length and 24 centimeters by width. I know what you're going to be carrying in that, who knows, but that's what they are nowadays with airline restrictions. So the question is, this value of x, this corner cutout that enables us to fold the flaps up to create a box, how can we determine the best value of x so that we have the maximum volume of the box? As you can see, the airlines have restricted us in the length and the width dimension, but they haven't restricted us um, in terms of the value of x, basically. So, kind of, how could we use that to our advantage to maximize the volume slash space that we have inside our suitcase when we fold this up into a net? Does everyone understand what the question is? Do you guys get what I've asked? I'm assuming no one's saying anything, so I think you guys are doing it. I think I need to show this onto the screen as well, so I'm just going to quickly go to a different tab and show this onto the screen. Okay, so this is the problem, by the way, on the screen as well. In case, for those of you watching on the recording, find the value of the corner cut length x to maximize the volume of the box formed from this net. So the corner squares, they're not actually part of the net, they're the cutout bits, which enable the flaps to fold up. So what is the length of that square that we need, basically, to maximize volume of the box? So how much are we cutting out? So in case anyone's a bit stuck, I'd give a bit of advice to start off with. So make sure that you start off with your objective function. So state what your objective function is and state what you're doing to it. So I've asked you to give me a value of x that would give me the maximum volume of the box that we form from this. So what is going to be your objective function and what are you going to be doing to it? And yeah, that's how you should start off. And I'll let you guys continue with that. I hope you guys have calculators. Um, if not, feel free to give your answer in like kind of like a method form where like you talk about derivatives, you leave it as like dvdx. You don't have to say what it is if you don't have a calculator, but ideally you'd get an actual real number answer for the value of x. I'm just gonna pause the recording just so we don't use up time waiting for solutions in the actual recording itself. There we go. Okay, recording is resumed. So just gonna paste the problem in here. Copy image. Okay, right. So here we have the problem. And I'm just gonna draw up my solution. Okay, so the pen is now there. Okay, cool. So with this box, what we have is initially to draw. Okay, there. So initially, we want to get an objective function. So we want to maximize the volume. So can anyone tell me what? Like I'm assuming you've got the objective function as the volume, right? So what is the volume? Can we get what the volume is? It's going to be length times width times depth, in case like anyone wasn't familiar with the formula to calculate volume. Yep, that's correct. So here we have 64, which was the length, minus 2x because we're cutting off x from both sides. Then we have 24 minus 2x, same reasons, but for the width. And then at the end, we're multiplying it by x because that's the height. You can imagine if we folded it up, x would end up being the height of the box. And yeah, that's how we work out volume. So it's pretty much all of this question is pretty much just A-level maths. You should be able to like do it. So if we expand out this, we can see that it expands to. I've done this on my calculator once before, so I'm just going to expand and simplify in one step to prevent us wasting time with things like you already understand, because we know how to expand brackets. So the volume then expands and simplifies to 4x cubed minus 176 x squared plus 1500 and 36 x. So this is what volume goes to. So initially, we need to write our objective function. So we want to say max, like maximize. I'm going to move this image away a little bit. Okay. So we want to maximize V, which is volume. So this is the objective. What? What are you saying, Shay? Oh, right. There we go. Cool. Objective. So now with this objective function, we can differentiate. So there are different ways of doing this. So now that we have the objective function, um, we can branch off and do it the different differentiation way. So we're going to call this method one. And this is the one we learned in A level. So dv dx, which is differentiating v with respect to x. By the laws of differentiation, we can say that's going to be 12x squared minus 352x plus 1536. Okay, right. And now we have this, we can, or we can simplify actually. We can simplify when we make this equal to zero, basically, because we want to find the um, turning points, aka the minima or the maxima, and you always do that by making the derivative equal to zero, as we've learned in A level. So I'm just going to simplify this a little bit. So I'm going to make it instead um, divide everything by 4 and make it 3x squared minus 88x plus 384 equals 0. So now we need to solve this quadratic. We need to see what are the roots of the quadratic. So does anybody want to give any solutions to what it might be? So we want to factorize the quadratic. I'll give you a hint. You don't need to use quadratic formula. This one does indeed factorize. Shay, what did you get for the factorization? Or like anyone else that might have done it by now? Okay, that's fine. You didn't factorize. What did you, quadratic formula? I'll just basically, if you factorize it, it gets. I'm assuming like everyone knows how to factorize a quadratic, so I'm not going to go into that. But yeah, this is what we get. So yep, if you expand this out, you'll find that it does give us the equation above, and yep, that equals 0. Therefore, the value of x that we get is 16 over 3, and x equals 24. I've just realized I missed out a crucial step of the optimization problem. I forgot to mention the constraints. So here we're going to say subject to x being greater than 0. And this is important because you can't have negative length. So you can't have a negative value of x. So that's our only constraint. In fact, that's our only design variable. So that's the only constraint we can have. So out of these two, one of them has got to be the global maximum. So how can we find out of these which one is the maximum, the global maximum? Mind you, we started off with a cubic, so the graph shape would look something like this. But how can we find this point here, which is what we're trying to find, the global maximum of volume? This goes back to actually the first session on differentiation, where we were looking at like directional derivatives and stuff. So what is the way to do that? Second differential derivative or common sense. Yeah. Okay. Yeah. That's how you do it. So Common sense can't be taken for can't be taken for as a prerequisite. So let's just do second derivative. So the second derivative would be d2v dx squared. Well, it can be given the constraints. We know that x cannot be 24. But the constraint was that x is greater than 0. Oh, I see. You've added in some additional constraints here, right? So that x cannot be greater than 24 because it's the length of the... Yeah, that's actually true. Yeah, let's add in some additional constraints. I didn't think of those ones before. But yeah, let's add in the constraint that... oh, okay. X has to be less than 12 because it can't be more than half of the shortest length that we have over there. So it can't be more than half of 24 because then we would end up with an overlap of x and we'd end up with like nothing on that side. So yeah, these are the two constraints we have. So it has to be greater than 0 and less than 24. So we can write that out as one constraint where we have a nice constraint here. 0 is less than x is less than 12. So this is our constraint that we have. It's purely derived from the problem. X is between 0 and 12. And based on that, it can't be 24, meaning that the solution is x is 16 over 3. And that would give us the optimal value for the volume. So now we will come back to this question when we've learned other methods like hill climb and simulated annealing and compare what solutions we get with those when we compare it with the solution that we got from actual like differential optimization. This can be considered similar to what we do with gradient descent. We differentiate and then we go to like the minimum point of cost. In this case, we're doing similar, but like it's the opposite kind of, so which is sounds weird. But it's the opposite of gradient descent because we're kind of doing gradient ascent here. We're going up the gradient, trying to find the maximum point of volume, which can be thought of as like the cost. So this is the best way by far to do it if you have a differentiable function. However, as we'll learn later, not everything is differentiable. So if you go back to our notes, okay, so let's close this one up now. So formulating optimization problems, I'm pretty sure I don't need to spend much time on this because we just went through one, but there are some things you need to keep in mind. Obviously, objective function, it's the thing you're maximizing or minimizing, that's given. And the constraints you write subject to, and then you give the constraints that make sure your solution is feasible. Okay, thing that I didn't discuss was what design variables are. So basically any variable that's inside your objective function, except like the objective function itself, is a design variable because it's going to be one that we alter to get a candidate solution. So for example, x is the only candidate solution. Sorry, x is the only design variable from the example we had because it's the only value that we could change in order to get a different volume. V, volume, does not count as a design variable because we can't directly change that. It's a dependent variable. It changes based on what x is. So x is the real independent variable that we can change. Similarly to partial differentiation, we can't partially differentiate dependent variables. Just like that, the design variables are just the independent variables of the objective function because that's what we're changing and measuring the effect of. The search space, what do I mean by the search space? The search space is the problem is the space of all the possible x values allowed by the constraints. So for example, with the problem that we had above that Shay solved, with this one, we have a linear search space, meaning that any solution with the optimization function, with the objective function we created, that was a Euclidean distance from any point on a coordinate axis to 0. That's the Euclidean distance. However, our search space is only this line here because any other point could be closer to 0. There definitely are loads of points closer to 0 than the optimal one we got for this. However, they won't be allowed by the constraints, so there's no point looking at them. Therefore, the search space is all the values of x that we are allowed based on the constraints. And yeah. Okay, so constraints. So there are different types of constraints. There are explicit constraints and implicit constraints. So explicit constraints are the ones that we've explicitly mentioned and can't be assumed. For example, in the previous case where we did the optimization of the net box thing, we can say that x being less than 12 was an explicit constraint because it's specific to our problem, and it can't be taken that we assume that we know that has to be x has to be less than 12. In fact, we missed it out completely at the start. Good thing Daniel came and pointed it out. So uh, x that's an example of an explicit constraint. Implicit constraints, on the other hand, are rules that must be in place by the problem definition in order for the solution to be considered feasible or even make sense. That is the example of x being greater than 0. That's an implicit constraint. It's kind of more assumed. It's assumed that length can't be negative, right? You can't have a negative length. Therefore, x being greater than 0 is an implicit constraint. So that's kind of what they mean and the example, which is why I got us to do a little example at the start. Okay, so um, you know what? We'll come back to this specific question later once we've done a little bit more. Okay, so local search algorithms. So you know what? Let's do this question. So basically, I have a question here because we've just learned about formulating. So I'm not asking you to solve this and optimize it. I'm just asking you to formulate the optimization problem in the correct format, such that we can, let's say, pass it into a optimizer uh, to solve it. So here is a graph. This can be like a Dijkstra graph or anything, and these are bidirectional edges, so you can traverse each in any direction across these. And the goal is to get from 0 to 6. How are you going to write this as an optimization problem? Mm, Shay is typing. Okay. I'm going to give you guys a couple minutes to write down and formulate this optimization problem. And then I will, I'll go through it again on the whiteboard live. Hmm. Okay, so let me start the solution. So just to make something clear with the objective function definition is objective function has two words to it, objective and function. So objective meaning either minimize or maximize, that's the objective, and then the function is the mathematical function that we're doing that to. So you can't say objective function and then just put a function in. That's technically incorrect. You have to say objective function, then minimize slash maximize, and then a function, aka the objective and the function. Okay, now that's clear. Let's get started with this. So what we want to do here is we want to minimize the total weight of the path to get from 0 to 6, as Shay said in the chat. So minimizing is our objective. So what we need to do now is write out our function. So write the total cost of any path, specifically between nodes 0 and 6, as a mathematical objective function. So here we have our objective function, minimize, and the function being d0x1 plus and the summation of this and plus d x modulus x. So right now that doesn't mean much to you because you don't know what the variables mean. But um, d is like the distance. Let's say d is the Euclidean distance between the two parameters or the two arguments that we provided. So d accepts two arguments, and it is the Euclidean distance between the not Euclidean. My bad. It is just the cost. Sorry, like the cost or the weight that we must traverse between the two nodes. So if you go back over here, for example, D02 would give us the value 6 because that's what we traverse to get there. Okay. X1 and anything that has an X subscript something is a series. That's actually our path. It's a sequence, an ordered tuple, right? It's a sequence that gives us the path that we're taking. So each node can be associated with um, like a sequence, right? So this is a slide definition. Find the solution or maximize more than one. This is the. Oh, I don't think the objective function include whether you're minimizing or maximizing. I think with the objective function, whenever you have a so basically what's been said in the chat is um, it does not include minimizing or maximizing and just includes the function. So you can if you just write a function that's just called a function. Um, So with an objective function, you can minimize objective functions as well. I think that's why you have to specify, at least for our exam spec, I'm pretty sure that you need to specify whether you're minimizing or maximizing. In reality, it might be like a technical nuance that, an objective function implies maximize and a cost function implies minimize. And I'm pretty sure we can take cost functions are minimized as granted, but an objective function, I'm pretty sure, can be maximized or minimized. Um, and it was in several cases in the slides, I'm pretty sure, especially with this, it was called the objective function, and we were minimizing the path. When we formulate the problem, that's where we put min slash max before the other. So I've specified, but it's not part of the objective function. Okay. No, given the context of the optimization problem, the function itself is the objective function. Okay, all right. I'll look into that later. I will probably put something into the slides based on like what the objective function implies. But either way, when you talk about an objective function, you have to say minimize or maximize, and then the function slash objective function, whatever you decide that later to be. But that's just very a technical nuance what we mean by the objective function. The gist of it is in the exam, you're going to have to write minimize or maximize followed by a function. Whether you want to call the function the objective function or whether you want to call the whole thing the objective function doesn't really matter because you're writing the same thing either way. Okay, cool. So the distance. So basically, these are the distances, and what we're trying to do is minimize this, right? Because we want to minimize the distance, the total distance that we're kind of traveling, and that would be done in the shortest path. So we start off from zero, hence the start. This is how you're specifying which node you're starting from, and then which node you're ending at. So the start node would be zero, and then you do it to x1, whatever the path decides x1 is going to be. So x1, the series of x, like the tuple, is going to be a randomly selected path. Not randomly, but it's going to be any candidate solution, right? It's going to be the path. And basically, what you're trying to see is with the path, is it like can it be minimized by looking at the neighbors, right? So changing the value of x and then looking at the neighbors. So that's what we're going to look at later in hill climb as well. So in this, after we look at the first node, that's the distance from the node 0 to whatever node is first on the sequence that we're currently analyzing. And here we have a summation of all the different nodes that were traversed in order, or visited more accurately, in order to get to our solution. So this gets us to the second to last one and sums all of their costs up. And then finally, we have the final one going to node 6, which is our destination. So this is how we specify our start node, our end node, and then the path in between that's taken as a mathematical objective function, which sums to the total cost of a path, which is at the end of the day what every pathfinding algorithm aims to minimize, whether it's A star, Dijkstra's, whatever. So this is always the objective function. They don't use objective functions, but this would be if they did. Okay, so the design variable. What is the design variable? The design variable is the vector x. So I'm just going to zoom out a little bit so you can see more. So the design variable is the vector x. Why is x a vector? Well, x is a sequence of cities or like nodes visited. It's an ordered list basically. I don't know why I put cities. This should be nodes. I think I was looking too much at the Romanian example that Leonardo gave us. So X is the sequence of nodes visited, and therefore can be thought of as a vector, as the nodes give us directions and size, and is given by the element. The size is given by the elements in the list. So when we do modulus X, we mean how many elements are there in the list, how many nodes have we visited to get here, and yeah. So that's why it's thought of as a vector. So this is actually the initialization. So we'll see that later on with algorithmic approaches, the key important constraints to specify is the neighborhood and the initialization. So that includes what type is the design variable. And here we've specified it's a vector. So that's always important to do. Make sure you make a note of that one because it can be easily forgotten. So such that the number of elements in this sequence is greater than zero, which means we have to go somewhere. The natural obvious way to do would be make it that x just doesn't go anywhere, there's nothing, therefore the cost would be zero, right? You have to make sure that we at least have something in the list, and all of the values of I. So I is another variable that we're introducing which is completely dependent on x, which is why we don't have to mention it as another design variable. So for all I in the set 1 2 modulus x, so how many other elements there are in the path, how many other nodes are included in the path that it's trying to look at, and xi, so x subscript I, is in what is in the range or the set 1 2 3 4 or 5. Note how we don't include 0 or 6 because these aren't included. We're not going to say x0 or x6 because we mentioned these explicitly as 0 and 6 when we're looking at the distance. So they're not included. So you'd always bar out the start node and the end node when you're looking at the sequence of in between, which is what x gives us. Okay, so now that's one thing, but now how do we get all these d, right? How do we get these d's? So to get the d's, we need to say matrix d of distances such that d. What's this going on? Well, okay. To get the distances, we need such that d between I and j would give you the cost of traversing I to j, basically. Any point to any other point, it would give you that cost or weight or whatever you want to call that number that is giving us between the two nodes. Only if I and j are both in epsilon. So what epsilon is just the set of all the valid transitions of the graph. So here we can see the graph. So the set of valid transitions would be one set. So it's a set of sets, basically. One of them would be 0, 2, one of them would be 0, 1, one of them would be 2, 3, one of them would be 3, 4, and so on. So we have to make sure, basically, that um, our algorithm does not just say that the most optimal way is to just go from 0 to 6, right? Because we haven't specified a cost to go directly from 0 to 6 because that edge does not exist. So it might lead to an error, it might assume it's 0, god knows what would happen, so we avoid it by only letting dij equal the cost of traversing from I to j if I and j are connected, if it's like a transition within the set of transitions. If it's not, if it's trying to do something where it's not allowed, then dij is automatically set to -1. You can set it to anything, it doesn't really matter, but I've used -1. That's normally what's used conventionally used when we're setting something to null. We say it's -1, aka it doesn't exist. So as you can see right now, we're now further and further constricting our search space. The more we constrict the search space, the better it is because the less the algorithm has to fiddle around and try and find different paths. So yeah, you'll see that using that later, we can now form the constraint. So we now define the design variable and we've defined what we mean by D. You have to make sure once you have an objective function, you have to definitely define everything that's in it. Otherwise, you lose marks, I assume. Subject to h of x being 0, right? If h of x, that's the only constraint we give. However, then as you can see later on, we've kind of defined what h of x is, so we're kind of including more constraints. So here's the notation that we use to write it. Subject to. Yeah, cheers. It's cursive handwriting, I think. Yeah. So h of x is 1 if d0 to the first node in our path we're trying to find is equal to -1, or if the last node to the one we're trying to get to is -1. If either of these distances are -1, remember what -1 means. -1 means from over here that the cost it found, right? It does that path, that edge does not exist, right? If that edge does not exist, it'll become -1. Henceforth, if we get either of these being -1, we then make the output of h of x, the function, as 1. And if you go back here, you can see that subject to h of x equals 0. So the only point where the solution will be considered a candidate solution is if it's valid in the search space, and anything with -1 here would not be, because h of x would be 1, which is against the constraint. The second one is basically, I've said for each, there exists I in 1 to the modulus of x minus 1. Basically, what you have to remember is um, none of the in-between transitions can be -1 either. So when we get to xi plus 1, if that transition is -1, means that we've made an illegal move. We can't get to some node that we've got to. So then it would also set h of x to 1, which would render that solution invalid. If these two things aren't going on, otherwise we set it to 0, which means we have a valid solution, and then that goes on to become one of the candidate solutions that we can consider when we're trying to find the optimum. So a lot of the solutions would be eliminated by the search space straight away, because most solutions, a vast majority of them, infinitely amount of them actually, would be like not within the search space itself. And then for larger graphs, so right now we have quite a small one where we can do stuff like this, where I've just like said all of the nodes in one single set. If it's a larger graph, for example, like all the restaurants in Birmingham, I don't know why you do that, but yeah, you can name the set of nodes instead of writing it out as a constant. So you'd say like G equals, and then followed by the graph, the set basically, and then name specific nodes in G by saying A in G. So instead of saying node 0 and node 6, I could have said this minus, remember minus in set notation is like a slash, minus a b or something like that, where then I'd go on to say a is in G if G was the graph, and b is also in G. So those would be the start and finish nodes, and I'd label them and say that they're inside the graph. So that's what you do for a larger one. Luckily, this was quite a small graph and I didn't have to do that. So that is the formulation of an optimization problem. We could very well actually be asked a question that looks like this, where you don't actually have to solve the problem, but you have to formally like write out an optimization problem in this format, where you have a clear objective function and what you're doing to it, where you define the design variables, the search space, etc., that your objective function is using, and then equally importantly, you say subject to and give all the constraints. Doesn't matter if it's implicit or explicit, you should still give all the constraints. Definitely explicit ones, because that's the whole point of them being explicit. So that this is how you would form an optimization problem, done on a simple example, but I've said here how you could generalize it for larger graphs as well. So does everyone understand the formulation of this optimization problem? Does anyone need me to go through anything? Does anyone have any questions before I move off? This is like probably as complicated as optimization, formulating an optimization problem would get. So if you have something like this, you won't be expected to actually solve and optimize it. Don't worry. That would be incredibly weird. If that would be impossible if they asked us. You get it? Cool. All right, let's move on then. So that is optimization formulation. Okay, next. Now we're going to move on to local search algorithms, right? So, what is a local search algorithm, aka optimization algorithm? So, right now, oh, Victor is a speaker. What's up, Victor? Oh, he's left the stage. Okay. If you want to talk, I don't mind. If you want to talk, come up on stage and talk, yeah? Um, So, local search is an optimization algorithm. So, currently we were looking at how to formulate optimization problems in a mathematical sense. However, now we're going to look at the algorithm that's actually used to solve the problems that have been formulated. So, what can we use to solve the formulations that we made above? So, um, the key things to remember about all local search algorithms, they operate by searching from a randomized initial state to neighboring states, kind of like gradient descent. In fact, I think gradient descent would actually count as a local search algorithm. So, yeah, that's for the record. Um, and these algorithms do not keep track of the paths nor the states that have been visited. This is beneficial and also detrimental. It means that they can get stuck in a loop where they keep visiting the same states again and again and not realizing because they don't remember that they've been there before. Kind of like if you have dementia, right? These you can think of these algorithms have having like dementia. They don't remember where they've been. But that is actually beneficial. They don't need to store that, so it's actually very low on the space complexity because they don't need to store everything that they visited in the past. They can like carefreely just roam around, and it does not matter if they like visit the same one again. So, but like they are designed so they don't do that, and we'll look at that later. So, yep, they use very little memory and can find reasonable solutions in large or infinite state spaces where it's unfeasible to, you know, look through everything because it's infinite. Um, they're used in many applications like circuit design, job scheduling, factory floor planning, I think, and yeah, other stuff. So, hill climbing. Well, hill climbing is a specific example of a local search algorithm, just like other examples we're going to look at, like simulated kneeling, gradient descent, etc. So, hill climbing is one of them, and it also has many variants that follow the same kind of path as hill climbing. So, the goal of hill climbing is to maximize an objective function and solve the same problem as gradient descent, basically. I've written it out here like this so you guys can understand what it's doing. So it's solving an optimization problem, kind of like gradient descent. However, instead of minimizing the cost, it's maximizing some objective function, right? And they're not implemented in the same way. So careful. So gradient descent and hill climbing are very differently implemented, and that's what brings them each of their advantages and disadvantages. So hill climbing, this is an important bit for later on, takes a single variable change. What are the differences? What between gradient descent and hill climbing? Yeah, okay. So yeah, that's what we're going to look at here. So one of them is obviously, well, in the gradient descent, you're descending, right? Whereas on hill climb, you're climbing. So one you're minimizing, the other one you're maximizing. That's probably the most major difference. Um, Other ones being that with hill climbing you don't differentiate, so it's useful for functions where you can't differentiate the objective function. When you have that, you'd use hill climbing. You can obviously reverse it and use the same process but to descend if you have a cost function as well. That's undifferentiable. Other thing is it doesn't use partial differentiation. Instead, it just changes a single variable and then measures how successful that variable change was in affecting the value of the objective function. So and it's also local search, so it doesn't. Yeah, that's pretty much the differences. Both of them are local search, but that's the differences with hill climbing and gradient descent. And I'm pretty sure we'll discover some more, and I'll remember more once we go through the process. So yeah, stay tuned as well. Um, so the process of hill climbing is we just generate an initial solution at a random point, any random value of the design variables, basically generate neighbor solutions, and move to the one with the highest value of the objective function. So the number of here are some caveats here. So just to remember, not really caveats, but like specifics. So number of neighbors, neighboring solutions can vary based on hyperparameters. So we naturally set hyperparameters, like with anything. We'll look at the hyperparameters later. Um, but it's typically correlated with the number of free parameters that are adjustable. So, for example, if we have an objective function with two design variables, let's call them x and y, we may have four neighbors per solution. So every time we look at a solution, so we start off, let's say we're doing a hill climbing, we get to a random initial solution. So a random value of x and y is given. What are going to be the neighbors around this? Well, it's going to be x plus 1 y. That's going to be one neighbor. We're going to measure the effect. Has that increased or decreased the objective? Then the next point is another neighbor, x minus 1 y. So therefore now we've incremented x and decremented x. And that's one of the free parameters. Now we just do the same for the other free parameter, which is y. So x, then y plus 1, then x, y minus 1. So those would be our neighboring solutions for a solution xy. And then based on whichever one has the highest objective function result, we'd go to that one and make that the solution, then work out the neighbors again, and iteration, so on and so on. You might be asking, how come we don't have a solution like x plus 1, y plus 1, or x minus 1, y minus 1? Why not change both of them, right? Well, it's because one of the rules of hill climbing, for simplicity and to like prevent too many neighbors, is a single variable change only. Otherwise, we could have all sorts of combinations, especially you can imagine when we have high dimensional spaces with multiple design variables, right? We'd have too many combinations. So only a single variable change. So you only end up with stuff like this. The hyperparameters, however, I was talking about is how much do you decrement and increment. So hyperparameter here would be set to 1. So we'd be incrementing it by 1 and decrementing it by 1. That's a hyperparameter, for example. Another hyperparameter could be how much you want to test it by. So do you want to do like one solution that's x plus 1y, then the next one being x plus 2y, and then doing x minus 1y, x minus 2y. So do you want to do more? Do you want to go more in each direction? Do you want to go less in each direction? And that all contributes towards what the neighboring solutions are and how many neighboring solutions we have, which naturally then significantly contributes towards time complexity, etc. So you have to set the hyperparameters carefully of hill climbing. But yeah, that's kind of an example of how neighboring solutions are generated. If no neighbor has a higher value of the current solution, or like than the current solution, I don't typo, than the current solution, we terminate. Tell the program to die. Otherwise, you repeat with a new biggest neighbor and just keep going on and on again until you reach a maximum iteration point, which you have to specify. Otherwise, you risk the program non-terminating, which is bad. Does everyone understand the process of hill climbing and how we generate parameters? How we generate, neighboring solutions? If it's a yes, I want to take us back to the example we looked at the start and put into real life practice how we can use that the box example, but implement hill climbing to to find the optimal value of x, which we got via differentiation as 16 over 3. So that is the actual optimal. So we're going to see how well does hill climbing compare to that. You wouldn't use hill climbing for that because you can differentiate, but it's kind of to simulate what would happen if you couldn't differentiate the function. So let's head back over to here. So here we said this was solution 1. Do we have infinite space on the right? I wonder, probably not. Okay, so let's make another one. So let's say this is now solution 2. Turn on the drawing pad. Okay. Right. Come on, turn on. Okay, right, that's on. Right. So now let's say we want to, let's move this away for a sec. I can just circle it. Okay. Oh, right, that kind of worked. Kind of didn't. Oh well. That's fine, we'll rub these out. Okay, so now, what is our first step with hill climbing? I want you guys to kind of like walk me through this as well, so I can check like we're getting this. So we've specified the optimization problem. So we have a specified optimization problem here. The objective function is v equals this basically, and we're trying to maximize it. And these are our constraints, and x is a length. So yeah, what is the first step? So solution 2, we're going to do this using hill climbing. Do we have any shouts? Anyone? What's the first step? Pick a random initial state. Yep. Yeah, good job, guys. So Shay and Victor. Victor, do you want to give us a random value of x to start off with then? What random value do you want to give us? 2. Okay, solid. Let's start with 2 then. So we have v is equal to 4 2 cubed minus 176 x squared. That's what, not x, sorry, my bad. 2 squared plus 100 and 1,536 times 2. Right, that was kind of painful to write. Okay, can anyone do this on their calculator? If not, I've got my calculator at home. I can do it as well. 4x squared, x cubed, sorry. Did people get 2,400? Because that's what I got. 2,400. Thanks, Shay. Good job. Cool. So that is what we have currently. So now what do we do? So that is our current solution. We'll label that with an arrow. So what do we do next? People are typing increment and decrement 2. Yes, good, good. So in order to do this, we need some hyperparameters. So Victor, since you are the algorithm, it seems you picked a random value. So why don't you give us some hyperparameters as well? What's going to be the step size? Victor, you there? 3. Okay, cool. Let's increment and decrement 2 by 3 in each direction. Well, okay. That's actually, I'm glad you've given me that actually because it will show something. So I'm just going to call it v of x because I can't be asked anymore to like, to, to, that looks weird. Let's just call it f of x because it's normal, right? But we're going to do f of 2 plus 3, f of 2 minus 3. So this gives us, just to prevent me from having to write that out again. So if we set the value of x to 5, basically, that gives me 3,780 for that. And if we set it to minus 1, I'm getting minus 1716. Now, can someone tell me something about this solution that we have over here? Is it a candidate solution? No. Why is it not a candidate solution? This will be good for the slides later, actually. So, not, yeah, exactly. So it's out of our search space because what was our search space? X is greater than 0. Sorry, yeah, greater than 0 and less than 12. However, here, the value of x was minus 1. Therefore, it's not even a candidate solution as x equals minus 1, meaning it's out of our search space and wouldn't be considered. So this is not real, basically. This would not be considered. Well, it is real. It's just it's not going to be considered. Okay, so yeah, that is bad. Okay, we're not going to do that. So we've got this solution now. So this is our only neighboring solution, and it's also the one that's higher technically. So because this is higher than 2,400, therefore we're going to go with um, this is our next solution. V equals f of 5, which equals 3,780. Okay, that's one iteration complete. So now we have to do the same thing again. So according to Victor's hyperparameters, we have to increment and decrement by 3. So let's go with f of 8 and f of, oh, well, actually in this case we already know what f of 2 is, so that's nice. We don't have to calculate it again. But I think it's still technically a neighboring solution. Well, when you get to the neighbor of a neighbor, that neighbor is still going to be the neighbor's neighbor. You get me? So that's why. 3072. I got for f of 8. I got 3072. Someone confirm that? I'm pretty fine with it actually. And this one is 2400, as we know from before. So which one's higher? Well, 3780 was in fact higher than 3072. So we've reached the end. 3780 is greater than 3072, and 3780 is greater than 2400. Therefore, no neighbor is better than current, and therefore x equals the one that meant 3780. X equals 5. What's 16 over 3 as a thing? Okay, well, 16 over 3 is roughly, well, it's not roughly, it's exactly 5.3 recurring. So as you can see, with hill climbing, we actually got really close. We actually got quite close. We were just 0.3 recurring off. So it's not too bad. Yeah, Shay's given a lovely illustration there of what we did with the gradient one compared to like the hill climbing. So this one, how could we improve? Well, the hyperparameter was 3. Normally we select hyperparameters that are much lower. For example, definitely between 0 and 1. You remember how we had the learning rate. The learning rate of gradient descent. Remember that? That determines how much step we take in the direction of the gradient vector for gradient descent. This is similar to that. This is similar to the learning rate. It determines the step size we take or the increment or decrement we make. So we have to make sure to set that hyperparameter quite low normally, but also not too low because of the same complications that we get with gradient descent of like getting stuck in local minima and all of that. So yeah, if we set that value to lower, if we set that value to, let's say, instead of 3, if we sent it to 0.3, we would have probably got 5.3 as the optimal, because it's the closest value of 0.3 to the real solution. So yeah, that's kind of how hill climbing works. I hope that's explained to you how you'd actually do a hill climbing question in practice in the actual exam, because the screen recording is just about to hit an hour and okay, recording's back. So I've just moved back to the notes now. So that was a live example of how hill climbing works, and we used it with a problem we've done with differentiation optimization right before that, and we compared it, and it's not too bad. Even with a high step size, it wasn't too bad. So that's how hill climbing works. Can you put your notes in the chat, please? What these notes? Do you want me to put that on now or like after the session? Well, I'll put these all onto the recaps whenever. Okay, yeah, I'll just put it on after the session just to prevent it like being in the chat and then like getting lost in the chat. I'll put these on. Don't worry. So hill climbing is therefore a greedy algorithm. And what does this mean? It means that it does not look beyond immediate neighbors of the current state, meaning it finds the quickest good solution rather than the optimal solution. And that's what greedy means. It's like trying to find the quickest good solution, quickest where it can get to, even a plateau or anything where the neighbors are lower than itself, right? It will say that is the answer, which leaves it very susceptible to getting. It's very susceptible to saying a plateau or a local maximum is the global maximum. So you have to be careful of that. So next, what we have is components that need to be set. So representation, how to store design variables. So this is something that you have to set with any algorithm. Once you have an optimization problem, you have to set these. So how to store them? So do you want to store them as an integer, which is for x, or do you want to sorry no do you want to store them as a float, which is what we used for x, or a real, or a double, whatever you want to call them in whichever language you use. That is what we kind of stored this x value as in our optimization problem with the box. You want to store them as a boolean. I don't know what kind of like what kind of optimization problem would use a boolean variable like yes, true or false. um, or do you want to store it as a vector, like we did with the pathfinding? Remember the pathfinding? We had x as the design variable, which is technically a vector, even though it was a sequence, but it has a direction and magnitude, therefore it's a vector. Um, so a good representation should facilitate the application of the initialization procedure and neighborhood operator. So all that's saying is just pick a good data type that works well with the rest of it. So initialization procedure is basically how you pick the initial solution. So you know how we for our current one with hill climb, we did a random solution, a random one to start off with. That's usually the case. However, that's not always the case. Sometimes we can use heuristics, such as the ones we saw in informed search, to pick the initial starting point. So, for example, last in our previous example, our initialization procedure was Victor. We used Victor as the initialization procedure. He gave us a number. But yeah, quite often you don't have Victor available, and you have to use a random one or a heuristic. Um, okay, so next thing we have is the neighborhood operator. Yeah, he was the initialization procedure. Okay, so next thing we have is the neighborhood operator, how to generate neighborhood solutions. So this is the step size. So again, in our last example, the last question with the box, we set the hyperparameters using Victor. So gave us the step size and the increment slash decrement we were giving. So that was set by the neighborhood operator was set by Victor. However, normally you don't have Victor available to set the neighborhood operator, and you need to set those hyperparameters yourself. But that's basically, in all seriousness, just how you get the neighborhood solutions as well. Cheers to Victor. Okay, so performance of hill climbing. So, how does this compare? So we saw it in our example we did ourselves. It was actually quite good. It worked. It the real answer being a solution of 5.3 occurring. It got 5. It's good enough normally. This is why it's greedy. It sort of comes across the best one it sees, and yeah. So hill climbing is not complete though. That's one of the major drawbacks. It's if anything's not complete, it's not reliable, because completeness is the like the property that a algorithm will find a solution if one exists. However, that's not always the case with hill climbing. So it depends on the problem formulation, which is what we did at the start, how to form an optimization problem. Remember, you form the optimization problem and then you pick one of these algorithms to solve your optimization problem. But the algorithms can only be as good as the formulation that you've done initially. Hence, it's very susceptible to bad problem formulation. It's also the randomness at the start. Um, it was that can also affect it, as well as the design of the algorithm, etc., etc. So it may not find a solution even if one exists. Optimality. How good is it at finding the optimal solution? Well, it's not optimal. Like we found that out ourselves with our live example. It just gave us it gave us close to an optimal, but it's not 5.3 recurring. It's not optimal. So it can get stuck in. It can also get stuck in local minima and maxima. Sorry, in a local maxima, right? Not minima, and that also depends on like step size, hyperparameters, etc. Time complexity. Time complexity is O of NMP. So what is MNP? Well, M is the maximum number of iterations we allow. N is the maximum number of neighborhoods checked, and P is just an arbitrary complexity that we say that the two processes above take to occur. So we say M or and N both occur in like P complexity, which takes O of P to generate. So I'm pretty sure that's linear. Yeah, so that would be like neighbors checked of each solution, and each of those solutions would take O of P to generate, like each neighbor basically. And then finally, space complexity, we have O of NQ plus R. Once you get to a big value, which why we use big O, we can trivialize the R, get rid of it basically, and we end up with O of NQ. However, we will still want to know what it is because it's important. So the solution takes O of Q. Um, so basically, the solution, right? That's the space that the solution takes is O of Q. Okay, it depends. Like that's not that can increase and decrease basically based on how much space the solution's taking. Um, which is why we're multiplying it by n, because n is the number of neighbors, and each of the neighbor solutions would take q space as well. And r just represents the space required to generate the neighbors sequentially. And that's trivialized and negligible compared to n and q. So if you take away one of them from the space complexity, just take away O of NQ. The R isn't really significant. And as with all algorithms, there are pros and cons when you'd use it, when you'd not. So, can rapidly find a good solution because it's greedy, right? Low time and space complexity, very good. Does not require problem specific heuristics, aka it's uninformed, right? So we don't need any heuristics or anything, it just does it without even looking at the whole problem space, which is something that we had to do with breadth first and depth first. And then start from a candidate solution instead of building it step by step, basically. So that's a rare possibility, but it's still a possibility that needs to be considered when you start off at the goal that you're at. Therefore, you only do one iteration. I don't know why that was in the slides, but it could happen. Okay, so cons. Why would you not use it? Well, you wouldn't use hill climb because it's not guaranteed to complete. It's not. It's not got completeness. You don't know if it's going to give you a solution, even if one exists. So that's a major drawback. Unreliable. Okay, and obviously it can get stuck in local maxima and plateaus and pretty much just stuff like that that we have with gradient descent as well. However, you might be kind of depressed to realize that um, hill climbing had a lot of children, and they are different variants of itself, slightly different, but very similar to the original. And these guys, so we have three siblings: stochastic hill climbing, first choice hill climbing, and random restart hill climbing. So out of these, we'll start off with stochastic hill climbing. So this variant randomly selects a neighbor that involves an uphill move. May not be the steepest, might not be the steepest, guys. It doesn't differentiate like that. Um, However, it just picks one of them that you know. We're getting in the comments that random restart is defo the middle child. Well, that's debatable. I think the eldest child is the best, and I think random restart is also the best for reasons we will come to. But let's finish with stochastic first, which I believe is the middle child, in my opinion. Um, so um, it doesn't pick the steepest; it just picks one of the random neighboring solutions that goes in an upwards direction. So it can't pick any that goes down, but if all of multiple go up, it'll pick a random one of those. And this depends on many factors like heuristics and steepness, however. And this basically converges slower than a direct hill climb. However, it can find higher quality solutions because it's less likely to get stuck in a local maximum. So you're kind of trading off the speed for a little bit of a higher chance of finding the global maximum. So you can imagine if with the one we did earlier with the box, instead of picking the one with the highest value each time, we just picked like any of them that were positive. So I remember first time we did it one with -1, which wouldn't have been the search space anyway, but that one would have been negative. It gave us a negative value of volume. Therefore, we discarded it. Would not have been considered, even with a stochastic hill climb. However, all of the positive solutions could have been considered. So instead of going to three, we could have gone to the one with five, and we would have continued from there. And all of them would have been equally considered. So you can see why it would take longer to converge because you're just kind of going randomly upwards. You're going upwards, but not in the steepest way. And yeah, that's basically how it's working. You can imagine it with the example we did in practicality. So then we come to stochastic's brother, first choice. He or like, I'm going assuming gender here. Okay, it come to stochastic's sibling, first choice, right? Randomly generates a single successor neighbor solution and moves it moves to it. Sorry, I can't read. If it's better than the current solution, um, if it's an uphill move, it keeps randomly generating solutions until there is an uphill move. And after a maximum number of tries or generating all the solutions, if it hasn't found an uphill move, it gives up and assumes that it's now the optimal solution, and yeah, that it returns that. The time complexity is lower, as not all neighbors need to be generated. However, before one is picked, which is good if when there's loads of neighbors to consider. If you have loads of dimensions, loads of neighbors, you don't want to have to like generate all of those neighbors before picking one. If you're only going to pick one, why not only just generate one? That's what first choice kind of said. First choice, kind of like the first child, is like saying like, oh, if I'm only picking one solution, why not just generate one solution? Why am I generating all of these solutions just to forget them after I pick one? You know what I mean? So it just picks a random uphill move. It only generates that one, and therefore it's the only one it can pick and moves. So it's slightly quicker, but also, it's less reliable because it is just generating one random neighbor and going to it if it's uphill, um, which is not necessarily going to be the best uphill to go in. It's basically stochastic if you think about it, but only generating one solution and then going in that. That would be the random one it picks, basically. And my favorite, random restart hill climbing. I love this guy. Right. So this generates a series of different hill climbing searches of the same problem, but from random initial states. And it stops when a goal is found. And if you think about it, basically the regular OG hill climber, right? OG hill climber is used multiple times, and this can be easily parallelized into the search space. You can have multi-threading, concurrent processing, parallel processing, lots of cores, all that good stuff. You can implement that with this. Um, you can implement this with the random restart hill climbing. And, yep, it's kind of like the BOGO sort, kind of random, but this is actually the only variant of hill climbing that is complete, has the property of completeness, rendering it to be reliable. Is this true in practice? Probably not. You'll see why it's complete. It's only complete because it'll just keep going with random solutions. And eventually, it'll generate a random solution, which is the answer. And yeah, that's why it's said to be complete. But This is normally the best one used in practice, not only just because it's theoretically complete, but also we now have modern computers that have parallel processors, we can have multi-threading, and we can have multiple hill climbs all tackling the same search space at the same time, which gets us a solution in record time. So this kind of pairs up, this variant pairs up and just has multiple versions of the OG hill climber. So yeah, that's how this one works, and that's it on hill climbing. Next thing we're going to go to is um, simulated annealing. So do we want to break or do we want to like bro is sponsored by random restart? Yeah, it is the best. It is the best. Trust me. Um, use the link in the description to get a discount on your first random restart hill start. Okay, so with stimulated. Why did I put stimulated? Simulated annealing. So do we want to break? Because we have been going for quite a while. Do we want to break or should we just continue? Should we do the rest of this in a different session? Like I kind of feel like we're halfway through right now, which is not good. So do we want to do this in like another session? Finish it off, or I don't know. Shay, you're the one to make the call there. Do you want to split this up into two optimization sessions? So, with a poll on the chat, we have decided to split this session up into optimization part one and optimization part two. So, yeah, in optimization part two, we'll look at simulated annealing, which uses physics properties like the Boltzmann distribution to simulate annealing, which is a process used to harden metals by heating them up and then gradually cooling them down, so their particles align with each other and form like an alloy, kind of, which is harder to break. I'm pretty sure that's how it works. And then we're going to look at other things like constraint handling and then different approaches to constraint handling, like the death penalty and levels of infeasibility. So that's the forthcoming attractions, guys. That's what's coming up next. Stay tuned, and I'll catch you guys in the next video.